Hello, welcome to EEE 117. This is Dr. Trey Stoops, and here we are continuing on chapter 12, where we will introduce LaPlace transforms as a tool for complicated circuit analysis. So before we get started with LaPlace transforms, we need to kind of review what we learned in Engineering 17 for time domain circuit analysis. So almost everything you've learned was always something related to time. V of t, I of t, right? P of t. The most basic things you started with was DC circuit analysis with resistors. So you have two resistors in parallel, you got voltage. You can figure out the current through here, through Ohm's law. And what type of math did we use? Honestly, it was just arithmetic. It was addition, subtraction, divisions, this type of stuff. Very, very easy. Anybody can do this. Next, we went a little bit harder. We added inductors and capacitors into the circuit. That became a second order differential equations, right? That now gets kind of hard. It is solvable, but it would take some time. Now, after DC circuit analysis, you started touching base on AC circuit analysis, but you didn't really learn much until you came to this course, right? We had a whole section of power engineering and AC analysis we just finished. We've briefly said it there. AC analysis with RLC components in the time domain is very, very hard. It's so hard that you typically don't learn it in circuit analysis because or any of your math courses, where did math course did you learn to do a second order differential when your input signal is sinusoidal, basically trigonometry? You never learned that. You learned when it was just a number, right? A decent component, sure, we could do that. And the reasoning why is this second order DE with trig is very, very hard to solve on paper. It's going to take you a very long time. You can use computer aided calculations through like MATLAB and stuff like that to help you. But remember, circuit analysis came way, way, way before computers. So we figure out a way to make this second order DE and trigonometry problem much easier, right? And one of the big reasons why is we figured out a different type of circuit analysis called frequency domain circuit analysis. So instead of using time domain as the variable that changes, we use frequency as the variable that changes. Now, the reason why, and we just said the reason why AC analysis is very hard, because you have second differential equations with cosine sine inputs, very, very complex. Instead of using time domain, and we use frequency, we can start making things easier. And honestly, we kind of already did that informally. It's called phasors from a month ago. Phasors is frequency analysis at its core. Now, the frequency is fixed to 60 hertz because we're doing power engineering, but no questions asked, it is still frequency analysis. And the main reason why you know is the impedance here of an inductor, Jx of L, is a function of frequency right here. Is J omega L. Well, omega is your frequency of the circuit in radians per second. So anytime you see omega or F for frequency, you know you're in the frequency domain. Anytime you see T for time, you know you're in the time domain. That's the difference. And if you remember, phasors analysis is a lot easier than second order differential equations. Phasors is just more arithmetic with imaginary numbers. But imaginary numbers and arithmetic is still much easier than differential equations. Okay, last question here. Phasors are locked into one frequency, right? And that's 60 or 50 hertz, depending if you're America or other countries. Okay, so we kind of already did frequency analysis fixed at one frequency. Okay, now the trick here is we might need to change that frequency. Okay. Now, before I go any further, everybody always asks, well, what's time domain? What's frequency? You know what the terms mean, but give me some real life examples, right? Because otherwise you don't know what you're memorizing. As humans, we can sense both time and frequency. Now, time domain viewpoint for a human is in my opinion, our mind senses time. Time is an honestly, time is an abstract quantity that humans made up. Cats, dogs, giraffes, they don't care about time. They just go bleh, and just go find food, right? But as humans, we quantify time as days, months, seconds, and whatnot. But in all reality, it's an abstract view, right? And we can measure time as our body grows older, the sun rises, sunset. There's quantities where we measure time, but it is sensed through our mind, not so much physical. Because if I touch something, I can't touch and say, oh, this is 13 minutes. That doesn't really make much sense, right? My eyes can't visually look at something and say hour and a half, right? Now we can maybe say, hey, this bread's been out for a week, right? But that's our mind processing what the visually it looks moldy and not moldy. Okay. So in my opinion, time is something we're innately familiar with because it's in our mind. We feel it every day as time marches forward. So we do circuit analysis in time domain because that's where we're most familiar. But it can get very complex. A frequency domain is instead of looking at an amplitude and a waveform of time, we're looking at different frequency levels. So frequency domain is we look at what's in front of us and we categorize it as a 200 hertz signal, a 1,000 hertz signal, 2,000 hertz, or 3,000, or anywhere in between. And we can make a graph where frequency is on the x-axis, and we could take a snapshot at every frequency and ask ourselves, what are each of these waveforms? So find the magnitude of each waveform at each frequency, and we can make this kind of graph right here. So for example, at 200 hertz, I know my amplitude is all the way up here. At 1,000 hertz, I know my amplitude is by half of what the 200 is, and so on. Okay, that is what frequency domain analysis is you're changing frequencies in the circuit and seeing how your amplitude changes over advancing as frequency gets higher or lower, right? Time domain is how does the circuit behave as time marches forward? 1 second, 2 seconds, 3 seconds, 4 seconds. Okay. Now, as humans, how do we sense frequency? It's harder for our brains to sense frequency, but our eyes and ears by nature is programmed by nature to sense frequency. What is sound? Sound is nothing but a frequency variations of the molecules moving in air. Right? Every time I speak, there's a sound wave or an air pressure that comes out my mouth, and there's a microphone right here. Right? I don't know if you guys see it. Yeah, there you go. Right? That picks up the pulses, right? So the microphone right here is a frequency collector. It does frequency analysis, right? Our eyes are frequency based. What are the different color bands? You learned this in middle school somewhere, right? Different color bands have a different frequency that we see. And red just means this frequency band, purple needs another frequency band. And our eyes can detect the different frequencies of light waves coming into our eyes. Because remember, our eyes literally takes in photons from the sun. The sun shines on the earth, and then it hits a red object, and only the only frequency that pops off the red object is a small narrow band of red frequency. And our eyes will pick up red frequency, and then it tells our brain, hey, red. Okay. So humans can sense both time and frequency. Frequency is just through our eyes and ears. Time is through our mind. And just, I guess, the way society has grown up, we're more sensitive to time from a thinking standpoint than frequency. But if you think about how colors are, maybe we are more sensitive to frequency. Okay, so it's just a good way to understand what is frequency and what is time in the world. Okay, and I like this graph. It shows kind of both ways. Now, another good example is AM radio and FM radio. AM radio stands for amplitude modulation. It's the old radios before like 1930s and 20s. The frequency was fixed. So this is always running at like 7,000 hertz or something, right? And don't quote me on that, right? Frequency is fixed at whatever frequency you're tuned the station in. And then the way we send information is a waveform physically gets bigger and smaller, right? We could go, a very big waveform is 10, A very small waveform is 1, and we could integrate, we could have a differential of 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 and send it out. So you can see in this waveform, you see there's a low, middle, low, high, high, middle, middle, low, high, really low, super high. This is information you could send to the radio or another carrier, and this can give either bits of data or voice output. Okay, but the big trick is the frequency set, and we have amplitude modulation. So what type of analysis will we use? Well, because the frequency doesn't change, we can't use frequency analysis. We have to use time domain analysis. See, time domain, as every second marches by, the waveform changes, the amplitude, right? So that is a convenient time analysis because every second is a different waveform, right? Or different amplitude. So that is, this AM radio will naturally use time domain analysis. Okay. Now we got more a better version of radio called FM radio, where that's frequency modulation. So for that, the frequency will actually increase or decrease to send information. So we might tune in like 104.5 megahertz, but within that 105 megahertz, we might modulate 106, 105. Let's say it's 105 point. Let's say it's 103.5. We might go up to 103.6 or go down to 103.4. And we can modulate within a small window of that frequency. And so as we modulate the frequency, we can send information. You can see right here, notice that the waveforms get closer together. That's the frequency increasing. Notice how it gets wider as the frequency decreasing. So a lot of today, even today's world, FM radio uses this modulation of frequency. Okay? The amplitude is completely fixed. So frequency is modulated, send information. Amplitude is fixed. So from a time aspect, the amplitude is not changing. So it's really hard to use time domain analysis to figure out what's going on. But the frequency is changing quite often. So naturally, looking at the frequency variation, we should use frequency domain analysis for FM radio, right? So that's kind of just an example of when would you use time domain, when would you use frequency domain, okay, for analysis. Okay. Now, honestly, no one uses AM radio anymore unless you're an amateur radio. 99.99% of everybody uses FM radio. All cell phones, all wireless signals use some type of frequency modulation because that's more advantageous. It's more efficient than AM radio signals. Okay, so the whole world uses frequency modulation. We could have a circuit right here with a filter. Now, we have our inputs and we have our outputs. We have a load, R2. The question is, if my frequency changes, how does this circuit change? And that's a very valid question. So far, we've always talked about how the voltage is fixed at 60 hertz or 50 hertz. And then power it is. We're not in power anymore. Okay, we're more in the communication side. You should expect your frequency to change a lot. Cell phone carriers, their frequency it goes up and down all the time as you're talking or watching videos on your phone. So for example, your input voltage will be fixed at 10 volts, but my frequency would change to 1 hertz, 1000 hertz, 2000, 3000, 4000, 5000 hertz. So as my voltage frequency changes, how does my load take that, right? That's information I'm sending. And we need to do circuit analysis. Now, one way you could do circuit analysis is we could literally look at 1000 hertz, take a snapshot and ask yourself, what does this circuit look like? Where the resistors don't change, but the X of C does. Remember, X of C is 1 over JWC. So we'll figure out where the impedance is, and then we could figure out our V in or V out over V in, or ratio, and look at the gain of the circuit. I can literally calculate V out if I have all these numbers. And what we'll see is we could redo it 2000 hertz, 3000 form, and if you remember, X of C, as the frequency gets higher, X of C gets smaller because the frequency is on the bottom of the radical. So it's 1 over JWC because W is in the bottom. As frequency goes up, the impedance goes down on the capacitor. So V out will get smaller as well. And the reason why V out gets smaller is as the frequency gets higher, this capacitor impedance gets smaller. So the current will short through the capacitor more than a resistor, right? Current always takes a path of least resistance. So at a very high frequency, this capacitor will have very low impedance, so all the current will just go straight through the capacitor and almost ignore load itself. Okay. So this is kind of what a varying frequency circuit looks like. And eventually we want to fill out this table. And the reason why we want to fill out this table is I want to see a trend. Okay, you'll notice as the frequency gets lower, V out gets lower, right? So this can help filter out high frequency noise, right? And so we'll learn way in the future, this is called a low pass filter. Okay, but we need to use frequency analysis to figure this out. So doing this is a lot easier because it's just arithmetic, right? We already did this before. Than using this second order differential equations with sines and cosines, right? Because all these input voltages are sines and cosines of varying frequency. I don't want to do this second order DE. No way. Okay, I'd rather write this chart. This is easier. And this chart is frequency analysis. This equation out here is time domain analysis, and that's a lot harder. Okay. So formally, we use something called a Laplace domain. Laplace domain is a frequency domain of the system. Okay, now Laplace domain is a mathematical concept where it just, don't ask me why, but by chance the mathematicians decided to put S as the variable, where realistically for us, S is nothing more than a frequency. So you can imagine S is really just omega frequency. Okay, it's just going to be there. So you could almost think about interchangeably. So how can we use a Laplace domain to help us? So we're starting in the upper left, we have V in of t in time domain. Now I want to get to V out of t in time domain. Now looking at before the previous circuit, we could use a second order differential equation to do this. It's going to be very, very hard. Okay, or we could do a transform called a Laplace transformation from time domain to Laplace domain in the upper right corner. Notice we go to capital Vn of S, where S is now a frequency. And we just use this fancy L bracket to say this is Laplace transform. And honestly, Laplace transformation is very easy. It's a table. You just look up the table, you just write the answer, you keep on going. It's almost brain dead, if you ask me. There might be a couple of tricks, but for the most part, the transform is not that bad. Once you're in the Laplace domain, to figure out your circuit analysis, it's pretty much phasors. It's very, very similar to phasors. And then, if you remember, phasor is just algebra. That's all it is, right? This is easy. It really is. It might be a lot of math. It might be a good bit of algebra, but algebra is still better than differential equations. And in the lower right here, this could be our answer. It could just be V out, the V out in Laplace domain or the frequency domain. That could be the answer that we need. And then a lot of times, honestly, in circuit analysis, because we're designing things in frequency domain, we might just stay right here, right? We could do a lot of analysis here. We could build circuits. We could end our work right here in the Laplace domain. But sometimes we need to go full circle back to the time domain. So we do have something called an inverse Laplace transform to go back. And again, this is just more algebra. It's relatively easy. So the question is, we have 3 extra steps. Laplace, so Laplace transformation, algebra and Laplace circuit analysis, and then inverse Laplace transform. So it's 3 steps of algebra. The question is 3 steps of algebra easier than a single second order differential equation? And the answer is absolutely yes. 100% it is. Go ahead and try. Be my guest. You're probably going to spend like 15 pages of paper trying to figure it out. Okay. It's easier just to do the hard work to do the transform and go back, right? Than just to go straight. And that's the whole reason why we're talking about this, right? We always want to make our lives easier in some form or fashion. Okay. So we kind of got a whole idea, recap, time domain circuit analysis, frequency domain circuit analysis. Anytime you're using AC voltage sources with inductors and capacitors, frequency domain will end up being easier. Okay, if you're just using resistors and DC voltage source, time domain is going to be easier. Okay, so let's start talking about how to set everything up. Before we get to LaPlace domain, we need to refresh time domain. Okay, we remember we have two types of voltage sources we see. We have DC voltage sources and AC voltage sources. DC voltage source is a flat line where V is constant. This could be like 15 volts, DC. AC source is alternating current, whereas V times sine of omega 1t or cosine of omega 1t. Right? Depends where you start. Right. Question is we need to quantify all this in the time domain before we can start converting over to Laplace domain. Okay. Another thing we need to keep track of is called a switch. Very common in circuit analysis, you see switch that turns on and off. It typically is at t equals 0, the switch turns on or turns off, but it basically starts a circuit. In the lab, when you hit the little on button on your function generator, that's the switch you're turning on. Now, when we do circuit analysis, it's easy as, okay, well, let's just start right there. Right when we turn on switch, let's start our work. But you really need to quantify it from a mathematical standpoint. I need to have a mathematical function to represent a switch, because when I do a Laplace transform, I need to take into account the switch. I can't just forget the switch. Okay. So we have something. It's called a unit step function. So notice you have a switch with a DC source behind it. It's 0 until t equals 0, and I turn it on. And then it goes from 0 immediately to V1 as the circuit turns on. So V is technically represented as V1 if time is greater than 0, or 0 if time is less than or equal to 0, it's off. Okay, that's the technical mathematical formula to represent a switched voltage source. Okay, this is formally called a unit step function because we're kind of stepping up. We're turning something on. So this is nothing more than a switch. That's all it is. Okay. Now we could formalize this as step function is u of t, where it could be 1 or it could be a k value. This is your voltage. It could be anything. It could be 50 volts, 100 volts. It could be sine of 37 volts if you really wanted to, right? So it could be any constant here. So, but remember, the trick of the unit step function is anytime you go past t equals 0, it turns on. So u of t, k times u of t is always equal to k if t is greater than 0. That's this right-hand side. K times u of t is always equal to 0 if we're on the left-hand side, where the border will say is 0 as well. If you're right, technically at 0. Okay. So this is typically whenever the circuit turns on, t equals 0, and then right afterward, boom, the voltage is on and the circuit starts operating. Okay, that's how we represent it. Okay, this is a very big building block in circuit analysis because we have to turn the circuit on at some point. We can't assume the circuit's been on for 50 years. Somebody turned it on this morning, which has to be represented with this unit step function. Okay. Now we could make it more advanced. Let's say we don't turn on as t equals 0. Let's say I come in the morning at 8 a.m. I don't turn the circuit on until 9 a.m. I need to take that into account, right? I have a delay, an hour delay. Well, how do I do that? Well, graphically, we could say a new step function we could represent with a time delay A. And I could say instead of everything turning on at 0, it turns on to the new A, which is, let's say, 9 a.m. Okay? And at 9 a.m., we turn the circuit on to K. Voltage. How to represent that? Any time shift in a circuit can be represented by saying t of minus the time shift. Okay. So I time shifted from 8 a.m. to 9 a.m. So it's a 1 hour delay. So I would say t minus 1 hour. Okay. So that I shifted the whole circuit over by some delay of alpha. It could be 1 second, 2 seconds, 50 seconds, whatever it is. Okay. And the circuit will now turn into this function will be k if t is greater than a, not 0. Okay. Actually, I have an error right here. I need to change. Right. I see it. And it's 0 if t is less than or equal to a as well. Okay. So that is what a unit step function is with a time delay. So here, the unit step function will turn on at t equals a, which again, it could be 5 seconds, 3 seconds, a millisecond. It could be wherever you want. Okay, we're just shifting it. We could make an off switch. What happens if the circuit has been on and then I want to turn it off, right? I want to open the switch, disconnect everything. Okay, we can do that. So all we have to do is reverse everything. We just have to say anything below when t is negative, it's on, and when t goes past negative to 0, it's off. Okay, I could do that. All we got to do is just put a negative in front of the time variable, and it'll flip the whole circuit. Or flip the whole graph around. Okay. So basically, here it will just say k, this new reverse step function is equal to k if t is less than 0, or if t is greater than equal to 0, it turns off. So it's on, and then at t equals 0, boom, it turns off, and our circuit's dead now. Okay. So basically, we want to turn it off at t equals 0, right? And of course, you could do the same idea as you could delay turning everything off. Instead of turning off at 0, I want to turn it off an hour later. So my A will be 1 hour delay or 5 seconds delay. Okay, so we're going to delay turning the circuit off. All we got to do is just say A minus T. So negative T means we're flipping the whole waveform over. So it's an off function. And putting this A right here means we're just delaying it a little bit. Okay, so this will read, it'll be the K value will be on as long as T is less than A. Once T becomes A, circuit immediately turns off. Okay. So we're just, it's an off, if it's an off switch that just got delayed. Okay. So you can see this we have two functions. We have the unit step function where something turns on, and the reverse unit step function where something turns off. And then we could delay it. Okay. Now, with this, we could do a lot of extra things. We could be really fancy in programming different waveforms. So for example, I could make a pulse waveform. This is a waveform where at 0, nothing happens. At 1 second, I flip the circuit on. So I'm literally flipping this switch in, the switch turns on for 1 second, and then the second, I immediately turn everything off. The switch is off. Okay, how do I do this? Well, mathematically, we could represent this as a value of k times u of t minus 1. So the first k times u of t minus 1 is this part turning on. See at 1 how it turns on? That's what this t minus 1 is. Okay. Now, once everything is on, this is now k value. Another trick we could do is after 2, if we have a k value, we could just subtract another k value and they'll net 0. They'll cancel each other out. And I could say, well, I will subtract another step function that starts at 2. And then you take 1k minus another k when they're both on, it will be 0. And you can see onwards the orange part. Okay. So it's just a mathematical trick where we could turn one circuit on and then cancel it. Now let's go do step by step and see how it cancels. So let's look at the blue part, the light blue. And somewhere between 0 and 1, let's put a f equals 0.5. So t equals 0.5 seconds. Let's analyze what this equation does. Well, it's k times where you have t minus 1. So if you have 0.5, so t is 0.5. So 0.5 minus 1 is a net negative 0.5. So the step function turns off. Okay. You then subtract k times another step function. If I plug in 0.5 at t, my overall u of negative 1.5 will turn off as well. So we have 0 minus 0 is 0. So obviously nothing happens. Now let's say at 1.5, so halfway between 1 and 2, the green bar, what's happening here? Well, we have k times u, and we're going to put 1.5 into t. So 1.5 minus 1 is a positive 0.5. So u of positive 0.5 is a 1. So we now have k times 1. We're going to subtract k times, well, we have u of t minus 1. Let's put 1.5 into t right here. 1.5 minus 2 is still negative 0.5. So we have a negative number inside the step function. It's going to still be 0. So from 1 to 2, notice we have k times 1 minus k times 0, which nets us a positive k value. So we're up top here. And let's say down at 2.5, we have the orange part where we should be off. Let's analyze what our function is doing. So we have f equals 2.5. Let's plug in 2.5. Well, k times, so we have bring the k over. We have u t minus 5. So 2.5 minus 1 is a u 1.5. That's greater than 0, so we have a positive 1. We're going to subtract right here minus k times u of t minus 2. We're going to plug in a t of 2.5, so 2.5 goes into t, and 2.5 minus 2 is positive 0.5. So this is also a 1 as well. We bring that down here, we have k minus k times 1. So overall, we have k times 1 minus k times 1. They cancel out to 0, and we have a flat 0 over here. Okay, so that's the idea of using step functions. If you're really smart with your patterns, you can make staircase functions, you can use ramp functions, you can do a lot of things. To me, the unit step function is like Lego building blocks where you can create a lot of different waveforms if you get really creative with your mathematical positioning. Okay. So for example, let's make this triangle waveform. We could do that with step functions, right? First off, I like to always define anytime you see a waveform change, that put a border right there and say, hey, this is one part. So for example, you see how it slopes up? I highlight it as blue. This is my blue part. And then it changes abruptly at 1 and goes back down. That's green. That's another part of the signal. Okay. So another way to solve this is let's make the blue signal by itself. This is a slope. Remember, slope is y equals mx plus b, or we could say f equals slope times t plus b, where b is the intercept. Okay. So let's make this slope and let's turn it on at 0 and turn it off at 1. So you can see this little square wave I made. This is a window function to turn a specific function on. So I'm going to make this blue slope moving up on at 0 and off at 1. And we could use step functions to create that. The green slope going down is going to be another slope. It's going to be vastly different from blue. We could then make another window function where we can make a step function that turns on at 1 and off at 2 and multiply these two together to kind of just chop the green waveform only between 1 and 2. So you have the blue waveform chopped it between 0 and 1 and the green waveform between 1 and 2, and you add them together to get the triangle waveform. That's a plan we can do. Well, let's try that. So first off, let's look at the slope. Okay, this is going to be the k. Remember I said k is a constant or a number? It could be a slope as well. It could be any function. So in this case, we're going to make a slope. So if you remember rise over run, like we're in elementary school again, we went up 2 and to the right 1. So it's positive 2 over positive 1. So 2 over 1 times t, that's our slope. The x-intercept, or sorry, they call it y-intercept. It's at 0, so then you don't have to add anything. So it's plus 0. So overall, this is just 2 times t is our function. This is our k value. And this is on between 0 and 1. So we can bring this down. Our k value is 2t. And we're going to multiply, open bracket, the window function. And the window function turns on at 0. So u of t right here turns it on. And then we'll cancel it and turn it off by subtracting the same step function at u of t minus 1. So we close the window. So everything in these big brackets, that's our window function between 0 and 1 right here. Okay, so we just made the first blue. Let's do the green function. It's going to be a little harder now. So first off, rise over run. We go down 2, so that's negative 2, and we go over to the right, positive 1. So it's negative 2 over positive 1. And what's our y-intercept. So we have to kind of trace it back to see what our original intercept is on the y-axis. Well, this one's easy. You can see it's 0, and then it goes to 2 as we go back. So, if x goes from 2 to 1, we went on the y-axis, we went from 0 to 2, and it's a flat line. So we could surmise when we go from 1 to 0, we're going to be up here at +4. If we literally just trace a line up like this, we're going to hit +4 right there. You can mathematically check it out, but visually it's easy enough. Okay. So our function mt plus b, m is -2, t stays with us, and b is +4. So our slope would be -2 times t plus 4. And our window function is between 1 and 2. So this should only be active between 1 greater than or equal to t greater than or equal to 2. So we'll say this second function is slope of -2t plus 4. So that's our big K value. And then we're going to have our window function of turning it on at t minus 1. Because look, we delayed it. We turning on at 1, not 0. So we have to put that -1 delay. And then we're going to cancel the window function by subtracting a second step function at t minus 2 to turn it off. Okay. And so all we have to do now is just add them together. So f of t is just a function of the first window plus a function of the second window, f of 1t plus f of 2t. Add them together, you have 2t, open bracket, u of t minus 1, close brackets, plus the second function, -2t plus 4, open bracket, u of t minus 1 minus u of t minus 2, close bracket. Okay? That's how and this, we're done. This is the exact mathematical definition of that single triangle waveform. Okay? So, I want to say, let's try to practice our slope functions and our window functions and use the step function and slopes to make this waveform. We already did 0 to 2. I already did that for you, but I'm adding this 2 to 4 part. I want to see how can you adapt to it. Okay. So notice there's going to be, if you do the method that I talked about, there's 3 major groups of waveforms. There's a positive slope from 0 to 1. We have a negative slope from 1 to 3 now. It was 2 in the previous problem, but we keep on going. So the second window we're going to look at is between 1 and 3. And then the third window is going to be between 3 and 4, and then it's 0 afterwards. So chop it off into 3 sections, do your slope function, find your window function, and let's come back in 20 minutes to see your answer and check everything out. Okay? So good luck, and we'll catch you in a little bit. All right, hello, welcome back to EEE 117, chapter 12. We're talking about LaPlace transform. Last thing we talked about was this unit step function, and we're doing an exercise of this full wave triangle function, and we're trying to represent this as slopes and unit step functions. So if you remember, the first thing we really need to do is we need to figure out slopes. So there's 5 different areas where 2 of them are kind of just like the 0 areas. So first off, anything before t is 0, so we have 0. T is less than or equal to 0. From 0 to 1, so 0 to 1, is we have a positive slope of 2, so we have 2t. And then from 1 to 3, we have a negative slope, so we have -2t plus 4. And that's from 1 to 3. And from 3 to 4, we're going to have a positive slope with if you think about going all the way down here, this is going to be on the y-axis a -8. So you have 2t minus 8 as the slope, and that's from 3 to 4. Anything after 4 is 0. So as the middle 3 are the 3 major functions we're going to look at. We could kind of condense it where we have 3 slopes. Positive 2t from 0 to 1, -2t plus 4 from 1 to 3, and positive 2t minus 8 from 3 to 4. So these 3 are the 3 zones we're going to make our functions off of. Okay. So here we got 3 slopes. Now we know our slopes. It's just a matter of taking these t equals off and on into a window function with our unit step building blocks. So first off, we have from 0 to 1. So we have u of t, which is starting on at 0, minus u of t minus 1. So we turn off at 1, and that is a slope of 2t. Next, we have a slope of negative 2t plus 4. That's the green part. It's from 1 to 3. So our window function is going to be u of t minus 1 minus u of t minus 3. So we'll turn on at 1 and turn off at 3. And lastly, from 3 to 4, we have the orange function, which is 2t minus 8. That's our slope. And then we're going to turn on at 3. So u of t minus 3, subtract u of t minus 4, where 4 we're going to turn off. So that's our third window function. And this is it, right? This is an acceptable answer to represent this whole waveform. Okay. So it's just building blocks. Once you get the pattern going and see the logic, it's just always making those window functions and form fitting whatever slopes we have. Okay. You can do sawtooth waveform. You can do sine cosine waveform if you really want to with this. Staircase function, square wave, pulses, anything can be represented with this type of predetermined window functions. Okay. So that's the power step functions where we could program pretty much anything. Another very important function we're going to use is called an impulse function. So the whole point of step function is when stuff turns on and stays on, or to create a window function when it turns on and then off. But what happens when we just have a single blip in the system? So let's say we have a system and then we just pulse it once, just touch it once and that's it. Okay. A common example will be, what if you have a pond that has completely still water and you take a rock and you throw it in? The rock hitting the pond is an impulse force. It hits it and the waves kind of peter out. But once the rock hits the water and goes to the bottom, there's no pressure on the water. It's just a one-time ding into the water. That's what an impulse function is in an electrical circuit. So there's a very common test we could do to any electrical circuit called impulse test, where we're just going to prod it for a split second turn. We're going to literally go boom on the nose for 10 volts just to see what happens. Okay, that's called an impulse function where you just boop it on the nose once. Okay, we could represent the impulse function as this delta t function. Okay, where again, it could be any length. It could be from 0 to 50 or 30 or 20, whatever you want. This will always be a constant, not necessarily a function, because it doesn't make sense to have a step function with a pulse, because this pulse is only on for one split second. Okay, so we'll have k times a impulse function, where if t equals 0, it turns on a k, and anywhere else besides 0, it's off. So it's literally on for a split second at t equals 0. Okay. So that is the impulse function. Just like the step function is, we could shift the impulse function. Let's say we don't want it at t equals 0. Let's say we wanted a delay of 5 seconds or 3 seconds. We could put this a delay. So we could delay by a seconds. And it's the same thing. You have k times impulse function with a t minus a, where the minus a is the delay in seconds. And it'll turn on if and only if t equals a at that 5 second delay or 3 seconds, wherever we choose. If you're not at that explicit delay, which I wanted, it's 0 otherwise. So this left-hand side is the original step function. This one at a is the new step function we made by delaying it by a seconds. Okay. So same time shifting property as a step function. Okay. Let's say you want a negative pulse. Instead of doing positive voltage, we do negative voltage. Well, that's easy. All you gotta do is just make sure k is negative. So instead of positive 10, let's make k negative 10. So we're gonna have a negative k times our impulse function, which again is k at t equals 0 and 0 anywhere else. And just this time k is negative. Okay. Now, the question is what's the advantage of using a impulse function? Well, this goes more to computer engineering and electronics, but a lot of your new computer system, especially your cell phones, we don't have analog sine waveforms anymore. we have something called digital sign functions or digital waveforms. So the olden days, we used analog circuit design where we would literally have this continuous time function like this. But it takes a lot of data to put every single millisecond of data into a memory point in your hard drive, right? Instead, what we could do is we could take samples of this sinusoidal waveform at 6 points and save the 6 data points. And then we could recreate this waveform we need later. And this is the basis of all computer engineering right here, is taking an analog signal and converting it into a digital signal. And the digital signal is nothing more than impulse functions at a certain time frame. Okay. This is exactly what an analog to digital converter does, if you ever heard of an A to D converter. Right. So we could represent this sinusoidal waveform with 6 impulse functions. We'll have 1, 2, 3 in a positive cycle, where 2 of them are at a magnitude of 1, and 1 of them is at the peak of 2, and then 2 of them at -1 and 1 at the peak of -2. And we could put this as a impulse function of t-1 to represent the first one. 2 times the impulse function at t equals -2, so that represents this middle one at the maximum. Then we got a delay of 3, so t-3, and that's a 1. And then we could do the bottom half, which is a -1 at t equals 5. So we have negative impulse function t-5. At 6 seconds, we got -2, so we got -2 impulse function t-6. And we got -1 at 7, where we have negative impulse function t-7, and that's the whole cycle. And then we just repeat this over and over and over again. Okay. So instead of writing sine and cosine, we just write this instead. And for a lot of computer applications, this is enough information you need to keep doing all your programming. Okay, so this is why impulse functions are actually really important on the computer side, because you're going to be seeing this. Because in the end of the day, it only takes 6 slots of memory to store this waveform. 1, 2, 3, 4, 5, 6. Right? If it was a sine function, it would take thousands of memory slots to fully form this waveform. Okay, so that's the advantage of using impulse functions. Okay, so in summary, remember we talked about time domain functions, what we started with whenever we're learning circuits, right? Anytime we had capacitors and inductors with cosine with AC systems, it's a second order differential equations with trig involved. It's very, very hard. I don't like it. It will be easier if we do a Laplace transform into Laplace domain, do some algebra circuit analysis, then find our answer in the Laplace domain. And we might just stay there. We might do more circuit analysis and build an entire circuit board based on this. Or we could go back to the time domain with an inverse Laplace transform if needed. Okay, so this, and going the long way around through the Laplace domain is quicker than doing a second order differential equation. And that's why we use that. Now, before we really start talking about swapping over, we needed to define 2 basic time functions. One represents a switch, which is our step function, which is u of t minus a, where you have it is the value of k where the switch is on when t is greater than or delay of a, and a can be 0 if you wanted to. So it's the original step function. And it'll be 0 if time is before our delay of a. Okay. Impulse function is a similar idea where you have a single ping of k voltage at t equals a, and it's 0 everywhere else. So it's just one little test point putting into the circuit. Okay, so that's all I have for today in terms of a very, very short introduction to the Laplace transform. This is explaining why we're doing it, kind of setting up the functions ready so that the next time we'll start talking about how to actually do Laplace transforms and other fun stuff. Okay, so thank you for showing up. I hope you guys have a good rest of the week and the day, and we'll catch you next class period. So see you later.